Hello again, everyone. Closing out track three of Iceberg Summit is Jinsong with Tencent, presenting building a batch stream unified lakehouse on Apache Iceberg and Tencent Cloud. Quick reminder that we will have time for a brief live Q&A after the presentation, so please be sure to use the Ask a Presenter tab to ask any questions that you may have and engage with your fellow attendees. And with that, join me in welcoming Jinsong. Take it away.
Okay, thanks, Max. And let me share our slides. Okay. Hello, everyone. Thanks for taking the time to join us today. I'm Jinsong. I work as a software engineer at Tencent for now. Our team are building a cloud-native Lakehouse product on Apache Iceberg. So I'm so glad to have this chance to talk about some work we are doing. Besides, I'm the original creator and the PPMC member of Apache Tomorrow. It is a Lakehouse management system based on open table format like Iceberg. I will give some information about Tomorrow too in this topic. Let's dive into the topic today, building a bench and stream unified Lakehouse on Apache Iceberg in Tencent Cloud. Okay, here is the agenda. First, I will give a review of the Lakehouse architecture in Tencent, then talk about how we build the unified Lakehouse on Apache Iceberg, the core feature of the unified Lakehouse, and the best practice for the unified Lakehouse. At last, I will give some information about the community collaboration and the future roadmap. I have to point out that when I say unified Lakehouse or unified table, I mean bench and stream unified Lakehouse and bench and stream unified table. Okay, let's begin with the overview of Lakehouse architecture in Tencent. Let's take the DOC product as the example in the Tencent Cloud. DOC is stand for Data Lake Compute. Our team is working on this. First, user uses the data ingestion service Ingnong to ingest data from multiple sources into the data lake product DOC, including application data, database records, and loads generated from mobile or web service. Then DOC provides the data lake service, including storage and computing. It uses object store service calls as its storage, Iceberg as its table format, and Spark and Presto as its compute engines. Besides, it provides permission management, engine management, unified metadata service, and data governance. Then users use VData, the one-stop big data development and governance platform to develop and manage their processing jobs. The processed data is used to build applications, including BI reports and machine learning models. That's a common journey for Tencent Cloud users using the Lakehouse solution. Now, we will explore how to build a bench and stream unified Lakehouse on Apache Iceberg. Here is a simple architecture diagram of the unified Lakehouse. From the bottom up, we divide the architecture into 4 layers, which is the storage layer, the format layer, the service layer, and the computing layer. In the storage layer, we use some common distributed storage service such as object storage service calls, self-deployment HDFS cluster, or AWS S3. In the format layer, we mainly use Iceberg, but also support Data, Hoodie, and Pymon if customers need them. In the service layer, we build our own catalog service to manage all metadata, optimizing service to maintain the Lakehouse tables, and the indexed service to speed up queries. In the computer layer, we mainly use DOC and the TC House in Tencent Cloud, but also support open source computer engines like Apache Flink, Apache Spark, and Apache Stories. We just have 40 minutes today, so we will focus on the format layer and the service layer. Here is an example how we use the unified tables with Smart SQL. In practice, tables are divided into two types: tables without primary keys and tables with primary keys. Tables without primary keys are used to store raw data from nodes and sensors, which is mainly ingested via streaming jobs and contain append-only data. In fact, they are just regular Apache Iceberg tables. Tables with primary keys are used to store aggregated data from streaming ETL jobs or database records ingested from streaming CDC jobs. They can accept insert, delete, and update operations in streaming process. We implemented a unified table format for this case. Yes, it is built on Apache Iceberg format, and we will find how we implement it later. Then you may want to ask why we do not use Apache Iceberg format directly in this case. The answer is that Iceberg still needs some capability for streaming process, not streaming read for now, and we try to implement it in the unified format, and it turned more features like the merging function here. Now, let's look at the Lakehouse service. Unified table service with these three core functions: compensation, cleaning, and some actions to speed up queries. The service will compare small data files, compare the delete files with the data files, and compare the change files with the base files, which is only for tables with primary keys. The compare service protects the table from poor query performance due to too many small files or delete files problem. The service will also display history snapshots, clean orphan files, and downloading delete files. It will also support configuring TTL on tables to display history data. The clean service helps the users to reduce storage cost. Besides, the service will also sort the data files, build secondary indexes like blown filter or bitmap, and generate table statistics. These actions help the computer engine scan these files or build a better execution plan to speed up queries on Apache Iceberg. What's more, the table service will automatically generate these actions, allocate resources, and make sure they are executed successfully. It is time to divide into more detail. Let's find out how we implement the unified Lakehouse. First, let's look at the structure of the tables with primary keys. It consists of two Iceberg tables, the change store and the base store. Change store is used to store the incremental data. In most cases, it is written to and read from by Flink or Spark streaming job. The data in change store will be merged into base store automatically. After that, data can be spared after several days. After it only has the insert file with append-only operation. Base store is used to store the baseline data. It is written by merge action and read in batch mode by engines like Spark or Trino. It has insert files and positional delete files. Before the change data merged into base store, you can use the merge on read mode to read all data in change store and base store, and the auto compensation action will make sure change data will be merged in base store within several minutes after being written. The merge on read mode and auto compensation action try to find the balance point of the read and write amplification issue. We implemented an auto bucket feature on unified tables to enhance compensation and merge on read performance. Bucketing is a common optimization for primary key tables. We will find the similar feature in Pymon or Hoodie. We divide the data into different buckets by its primitive value, both for change store and base store. Then we can only compare the data in the same bucket. It reduces a lot of cost in the compression and merge and read process. We do not require the base store and the change store to have the same number of buckets and allow dynamic adjustment of bucket number based on runtime condition. For the base store, we keep the total data size between 1 GB to 2 GB per bucket. For the change store, we focus on the writing throughput. Keep each bucket receives at least 1 MB of data per write. The system will dynamically optimize bucket layouts based on real-time workloads. Here is a diagram about how the unified table supports streaming features. The streaming write job appends data to the change store in a append-only way. The change store not only stores the data, but also the operation type, such as insert, delete, or update. The streaming read job continuously monitors the table for newly committed snapshots. Upon detecting a new snapshot, it reads the newly added data and processes with downstream processing. The automatic compression service will merge newly written data from the change store into the base store, like every 10 minutes. The merge engine will not rewrite all insert files each time it uses the merge and read write mode in the merge process. When merging the change store into the base store, we implement different merge functions, including replace, partial update, or aggregation. The replace merge function is the most common one. It overrides base store by change store based on the primitive value. The partial update merge function is similar with the replace, but it overrides specified columns only. So you can create multiple jobs to update different columns, which is very useful in the streaming join case. The aggregation merge function overrides data after aggregation computing between the old value and the new value, supporting many more maths and count, and so on. The open merge function feature gives more possibility to the unified table, enable it to support a wider range of use cases. Let's go back to the unified table service part. Here is the architecture of the table service. The most important model is the intelligent storage service. It provides REST API and web frontend to the end users or other applications. Besides, it has more models like the table runtime manager, table optimizing manager, table matrix manager, and optimizers manager. Table runtime manager discovers new tables after they are created, refreshes metadata when new snapshot is committed. Table optimizing manager generates new optimizing jobs when tables meet some trigger condition, like too many small files or delete file size reach this threshold. Table matrix manager receives table matrix from computer engines like Spark or Flint, which is used by other models like optimizing manager or table runtime manager, helping them do a better job. Optimizer is where the optimizing job is executed. The optimizer manager keeps the optimizers alive and schedule more when needed. Optimizer is stateless and can be deployed in multiple modes, like running in a Flink job or Spark job or a Kubernetes pod. Matrix reporter is an extension in the computer engines. It connects all table scanning and committing matrix and sends them to the storage service. Okay, let's explore some best practices for the unified Lakehouse. Here is a real-world example from one of our users. They built a Lakehouse cluster to analyze both database records and business logs, building their AI reports and AI application. They used to deploy a Hadoop cluster, use Hive for data storage, DataX for data ingestion, Spark for data processing, and Presto for data analytics. Now they want to move their infrastructure to the cloud and upgrade it if needed. A big change after migration to the Tencent Cloud is we replace the Hive tables with Iceberg tables. Iceberg tables are built on object storage service and provide streaming process capability. So we use Flink jobs for data ingestion for now, and the data latency has been reduced to minute level. The user save 30% cost after migrating to the cloud because of the nested resource usage and serverless service provided by Tencent Cloud. Besides, after replacing Hive tables with Iceberg tables, the end-to-end data service latency improved from days to hours. Thanks to the streaming process and high-performance query features provided by Iceberg. Here is another use case about building bench and stream unified pipelines. Their AI application needs extremely low data latency, require minute level freshness. In the past, they had built two pipelines, the streaming pipeline and the bench pipeline. The streaming pipeline uses Flink and the compute engine with Kafka storage, writing process data to the to-do, and using Impala for analytics. The bench pipeline uses Spark and the compute engine with Hive storage. Keeping two separate pipelines costs a lot. The user now unifies the bench and streaming pipelines on the unified table with its great streaming compatibility. They save 60% cost after upgrading. Finally, let's take a look at the community collaboration and the future roadmap. Our team keeps a close collaboration with open source communities like Apache Iceberg, Apache Amoro, and AutoMQ. As a heavy Flink user, we kept improving the Iceberg Flink connector, implemented some secondary indices with plan to contribute them to the community. We also aim to participate in the ongoing materialized view implementation. We also greatly appreciate the data optimizing functions provided by the Apache Amoro project, which enable us to build cloud service on it. Furthermore, we plan to contribute some of our extensions back to the community, such as implementations for table statistics and partition statistics, as well as some enhancements for mixed format tables. AutoMQ is another interesting open source project that enables Kafka with DataNet use case. It provides automated ingestion capability of Kafka data into Iceberg tables, helping us provide a zero ETL ingestion service. Our next step will be supporting second-level data latency, processing and implementing the materialized view. We plan to replace the change store from Iceberg table to some storage system supports lower data latency, such as the message queue or cache system like Kafka or Redis. In that case, we may support even lower data latency like second level. We will also implement materialized views based on Iceberg or unified table, supporting multiple refresh frequencies, including second level, minute level and hour level. The table service will be possibility to refresh the data in the materialized view. Oh, that's a great presentation. Thank you all. That is all I want to share today, and I'm happy to take any questions. And welcome to use our product or join the Iceberg or Amoro community.
All right, I'm going to give it a couple more seconds for anybody that might have any questions. We still have 25 minutes left of our presentation, so please don't be shy. I just got one. Can you expand on what technologies and processes you have in place to process sensor data without primary key?
Okay, in tables without primary key is much easier to use. We use Flink to ingest the at first we send the sensor data to the Apache Kafka and create a Flink job to ingest the data from Kafka to the Iceberg and use the optimization service to compile small files produced by Flink. And then you can use Spark or Trino to query this table, and its performance is good. So it's quite simple. When it's a much simpler sense.
Okay. And Joshua asked, is the indexing to handle equality deletes?
Yes, equality delete file is a big problem for Iceberg tables. We have optimization service to complement the equality delete files with data files and transform the equality delete file to the positional delete files. I'm not sure is what you want to know.
No, he continued on. He asked, is the base table merged from the change table with either Spark or Flink? Flink, Flink.
Okay. Flint is much popular in China, so and we have a product named Oceanus to help users manage their Flint jobs. So they are familiar with Flint, and but Flint connector is not familiar by Chinese users. That's the reason.
Gotcha. And Krupali asks, what's the motivation behind using Flink instead of Iceberg sync connectors for ingesting data from Kafka to Iceberg tables?
Okay. I think I answered this question
Previously.
first. Yes. So I want to answer the last question. Is the base table merged from the chain table with Spark or Flint? Okay. The merge action is processed by the table service, so you can use Spark or Flint, both okay.
I'll give it a few more seconds to let some more questions come in. But thank you to Diego, Josh, and Krupali. All right. Not seeing anything in the chat. So if there's any, oh, sorry, oh, no, that was an old one. Okay. Yep, that's it. So me go ahead and end this. If there's any other questions, please enter them now. But want to give a big thank you to Jinsong for his time today. As a reminder, all sessions will be available on demand within an hour at the end of the event. But thank you guys so much for all. Oh, sorry, just had one more question in the chat. My apologies. One from Marty. Have you looked into any other options for NRT capture of CDC?
Okay, so capture of CDC. Flink CDC is a project to help us transfer the CDC data from database, and it's very popular in China now because Flink community is popular in China. I'm sure there is other tools to transfer the nodes from the database and generate the CDC data. So use just what you familiar, and that is okay. Near real time. Capture of CDC is a common usage in database database technologies, and MySQL bin node is an open format for all their users. So fetching the nodes and decoding is not a problem. But for some closed source database, it's a hardware tonight or some other.
Sound good?
Yeah.
Awesome. Thank you so much, Jinsong, for a great presentation. I believe that's all the questions that we have today, unless anybody has any last minute ones. But thank you guys so much for joining. Another reminder that all sessions will be available on demand within an hour at the end of the event. Up next, we have our final session of the day, which will be a replay of the closing panel from the in-person session in San Francisco. So really exciting stuff. But another thank you to Jinsong for his time today. Please reach out to him if you have any outstanding questions. But thank you so much for your time.
And thanks, Matt, and thanks all. Thank you all.
Thank you, everybody.
Bye.
See you next
Bye.
time. Bye.